Okay, today what we're going to do is we're going to go back to our discussion on the electric dipole and look at some of its oddities and to make comparisons. And this is going to lead up into a discussion on method of images. So recall, if we place a positive charge on the z-axis, okay, so this is a representation of our z-axis. This will represent our positive charge, our coordinate system, and then since it's a dipole, an equal and opposite charge down below. And let us assume that the charges are a distance d over 2 above and below the z is equal to 0 plane. And I'm going to need my eraser. Let's take this out of the system. Okay. Now our task is to, so this will be Q, and this charge will be minus Q, and we will assume that Q is a number greater than 0. Now we want to draw the field lines. We see that there's a high degree of symmetry around the z-axis. So whatever occurs on one side of the z-axis must occur similarly on all sides. And we know that field lines do not cross, electric field lines. If they did, if two different field lines cross, the crossing point would be an indication that both of them have the same number. And that's not possible. You can't have two different solutions at the same point. It would have to be different solutions. Consequently, our field lines can't cross. And if we are careful enough, we see that our field lines look something like this. And I'll put it in red. It won't show up as nicely, but something like that. Now we're going to take a slice right at the position where x is equal to 0. And we're just going to look at that plane. These field lines evolve all the way around the z-axis, and they look like, I don't know, some type of shell. So consequently, let's redraw it just for clarity's sake. So now we only have two axes. This will be our z-axis. And this will represent our y-axis. And we are going to place, well, nothing yet. And we're going to draw our field lines in this x is equal to 0 plane. It's just our slice in space, if you like. And we're going to redraw our field lines. Okay. And using our convention or philosophy of electrostatics, The field line originates from a positive charge and terminates on a negative charge. So we can put orientation in as well. And let us just put a dashed line for the x is equal to 0, the z is equal to 0 position. And that particular position or plane, if you like, is perpendicular to our paper. So I can't draw it too well. There. Now we look and make an observation. We see that in the z is equal to 0 plane, our field lines exhibit a 90-degree behavior. And it should exhibit that behavior because there must be symmetry above the axis as there is below the axis or below the plane. Furthermore, we know from our discussions on potential that the electric field is equal to the negative of the gradient of the potential. And recall that the gradient of the potential dotted into dl can give you a difference in potential that's equal to 0. Here, dl is moving perpendicular to our surface. This would imply that the gradient along that surface must be, the gradient is pointing also perpendicular to that z is equal to 0 surface. Its dot product. Okay, let me repeat that again. Delta V is pointing perpendicular to this z is equal to 0 plane. We are going to allow dv to be positioned at any point on that z is equal to 0 plane. Since they are orthogonal to each other, we see that the difference in our potential must be equal to 0, and consequently we identify this particular surface as an equal potential surface. And that is the z is equal to 0 plane. It's spanned by the vectors, the x vector and y unit vectors. Okay. So that's one observation. Another observation is that the electric field points in the direction of not an increase in V, but because of that minus sign, in the decrease of potential. Our upper charge is a positive charge, our lower charge is a negative charge. We observe that our field line should go from the positive charge to the negative charge. And that's exactly what the arrows are indicating, based on our philosophy of electrostatics. Now we're going to play a game. And that particular game is, if this is an equal potential surface, can we slice it up in such a fashion that we can place a metal surface in its place? In other words, all metal surfaces, planes, wires, etc., are equal potential surfaces. By the nearly free electron model, the field at any point inside this particular geometry is always 0, the electric field. at least from electrostatics point of view. From a time-varying point of view, we get into a different type of discussion. Therefore, if we were able to take a piece of metal, copper, aluminum, gold, doesn't make that much difference for electrostatics, as long as we can slip it into the z is equal to 0 plane and allow that plate to be large enough to go to plus and minus infinity with respect to x and y. So consequently, what we have now is a equipotential surface, which is the form of a piece of metal. Let us plot the electric field lines for this piece of metal. And we see that the field lines have the exact same configuration. Because it's an equipotential surface, the field lines must terminate 90 degrees to that surface. And there's symmetry on both sides. Since our metal cannot support an electric field, we could, if you want, extend the metal all over all space, or say that our metal is of finite thickness and grounded. So there is a sea of free charge somewhere that we can draw that charge from so that it can cancel out the void of free charge inside the metal, giving rise to a charge distribution over the surface of the metal on one side and nothing on the second side, because the void of an electron will be filled with an electron that we pull from ground. If our plate extends to plus and minus infinity, then we state that our plate is grounded, and has enough charge that you will not be able to tell the difference when the charge redistribution takes place. So consequently, this particular problem, trying to solve this problem, is quite a difficult problem. Question, why? Because you know that your field lines terminate on charge. They don't terminate on the metal, they terminate on the charge in the metal. Consequently, if we were to look at the charge distribution over that surface, we would anticipate that if we were just under and on the axis of our initial positive charge, we should have the greatest concentration of electrons on the surface. As we move further away on the surface, we see that the concentration decreases. That's a complicated problem because we don't know what the charge distribution is or how the charge is distributed over that particular plane. So consequently, let's work backwards. What if we take the plane out of the system and go back to our two-charge system? We get the same exact field configuration, except here we observe that there's no fields in this region. Consequently, we can make use of what is called the method of images and put a fake charge in our system in such a way that it generates the correct field lines in one region of space that is of interest to us, and in another region of space, we will assume that the fields are identically equal to 0. So consequently, going backwards now, we will incorporate on our z-axis the original charge and the image charge. The image charge is equal in magnitude but opposite in sign of the charge Q. So this is not going to work for us. It's equal in magnitude and opposite in sign. Consequently, that's going to give rise to minus Q. There. And this gives us the field configuration that we want to solve for in the region of space z greater than 0. This is denoted as the image charge. And this model is denoted as the method of images. And it takes a complicated problem and transforms it into a more simpler problem to solve. Okay, with that piece of information in mind, we're going to go back and solve this particular problem for a plate that is of infinite extent that's located in the z is equal to 0 plane. We will assume that our charge is a positive charge. And the problem statement that we are looking for is a point charge. We want to actually determine the field determine the electric field above a perfectly conducting. It could also be good conducting. Infinite in extent. Planar slab. So here's our medium. And we will have a positive charge existing on the z-axis, which we will define as being equal to q. And the distance of separation between the origin and where charge q is, we will define as being equal to d divided by 2. This goes off to infinity in both directions. This one as well. And same thing for the back side. This is minus infinity. And we want to calculate the electric field based on the potential. So we are going to use method of images. We're going to remove the plate from the z is equal to 0 plane. And remember, it's a slab, so it's actually got some finite thickness to it. We're going to remove the entire plate. We have our original charge. And now we're going to add in our image charge, which is of opposite in value, or opposite in sign, equal in value. And we'll define that image charge as q sub I, and our original charge is q, and q sub I is equal to minus q. For this particular problem, we want to calculate the electric field at all positions in space, large, compared to the distance of separation between our two charges. So let's identify the distance between our two charges with respect to the z is equal to 0 plane. This we will identify as d over 2. This is exactly what we had over in our original statement. And our image charge is located the same distance below the plane along a straight line that connects the image charge and the original charge, and that line must pass through this surface at a 90-degree angle. Okay. Now let's pick our point of observation. Our point of observation is supposed to be at a position r sub p where the radius in a spherical coordinate system is much larger than the distance of separation between the two charges. Consequently, we can identify what that position vector is. That's going to be equal to r sub p times the radial unit vector, function of theta sub p and phi sub p. Okay. Let us also draw the vector, the relative position vector from the positive charge to our point of observation. And remember, this charge is very far away. Since it's very far away, we almost see that the relative position vector, we will call this r sub 1, is pretty close to being parallel to the position vector of the charge. And the same thing for the relative position vector between the negative charge and our point of observation. So consequently, I should be able to fit a triangle in here with 90 degrees to show that the distance, and I'm going to take off the vector notation. Maybe I'll leave the vector notation on, and we'll just say this will be r sub 1 in the r sub 1 direction. And this will be equal to r sub 2, which is equal to the magnitude r2 in the r2 direction. Consequently, we observe that the length from this triangle line, dashed triangle line, 90 degrees, to our point of observation is going to be approximately the same length that goes from our original charge to our point of observation. That is, r sub 1 is going to be approximately equal to r sub 2, which will be approximately equal to r sub p, at least in magnitude. In the same fashion, we observe that this extra length here can be related to the distance of separation. This angle here we can identify as being equal to theta, and consequently that's the same angle here, and these thetas are all approximately equal to each other. Therefore, we've got a 90-degree triangle, and this distance, r sub 2 minus r sub 1, can be re-expressed as being equal to approximately the distance of separation times the cosine of theta. This is not a differential, this is actual distance that we see in our picture over here. That's this distance right here. There. Okay, with this little bit of geometry in place now, let us look at the total potential. Making use of the method of superposition, the total potential V is equal to the potential due to our original charge, and we'll call that V1, plus the potential due to our image charge, which we will identify as V sub 2. The potential due to our image charge, we can make use of the concept of Coulomb's law, or the potential due to a point charge. This will be equal to charge Q over 4 pi times the permittivity of free space times the distance, r sub 1. Minus, this minus sign comes about because we have an image charge which is of the opposite sign of our original charge. So that's going to be equal to minus Q over 4 pi times the permittivity of free space times r sub 2. Pulling out like terms, this is going to give rise to Q over 4 pi times the permittivity of free space times the quantity 1 over r sub 1 minus 1 over r sub 2. Finding a common denominator, this will give rise to our constant term, Q, divided by 4 pi epsilon naught times R sub 2 minus R sub 1 over R sub 2 times R sub 1. Going back to our geometry, we can relate the relative position vectors to our position distances, if you like, to some type of geometry associated with our two-charge system. So consequently, this is going to be equal to our charge Q divided by 4 pi epsilon naught times the quantity upstairs, the distance of separation between the two charges, times the cosine of theta downstairs. This will give rise to the relative position, the position vector of our point of observation squared. Okay, let's keep going forward. We see what we're looking for is it possible to determine and to write an expression for this dipole in a coordinate-free manner such that we can use it as a law. So let us define, and this is a definition, script P vector to be equal to Q times times the vector D. This is denoted as the electric dipole moment and D has a name. It is denoted as the electric dipole vector length. So this is D. And this will be P. And Q is just the charge itself. When you see a cosine, what does that remind you of?
The horizontal?
No. What does a cosine remind you of? Who's your friend?
Dot product?
There you go. So it behooves us to try to get rid of this cosine theta term. And actually, that's the point of observation, so we'll say theta sub P. And re-express it in a way that doesn't require a coordinate system. Well, we see that the D, the electric dipole vector length, if we define it as the vector length pointing from the negative charge to the positive charge, and go back to our coordinate system, so we'll add it on to our coordinate system here. This represents that special electric dipole vector length. We observe that the dot product between D and the radial unit vector will give rise to the cosine of theta. So consequently, let us rewrite it and then demonstrate what we're trying to say. We have our dipole moment, and we're going to dot that into the radial unit vector, which is pointing towards my point of observation. And this is going to be equal to the dipole charge times d dotted into this radial unit vector. And that in turn is going to be equal to the charge q times the distance d times the cosine of theta sub p. Consequently, we can re-express our potential V at our point of observation. And remember, in our approximation, and that approximation comes about because we use this type of picture, we are assuming that the position of our point of observation is much, much larger than the distance of separation. So that's where the approximation comes in.
Are you pointing at something right now?
Go ahead.
Are you pointing at something right now?
There we go.
Okay.
This particular picture
Gotcha.
is the picture that has the approximation in. When point P goes very, very far away, these three lines become more parallel to each other.
Okay.
And consequently, we can then identify a distance, the amount of distance on line R2 that's different or extends beyond the amount of distance of line number 1. These lines are the relative position vector magnitudes. And consequently, we were then able to identify that and relate it to the distance of separation and the cosine angle. So this is the approximation that we are imposing inside our problem that we're using to solve this particular system. Okay, so now we want to combine everything together, and our potential can be expressed as the dipole moment dotted into the radial unit vector, which is a function of a spherical coordinate system divided by 4 pi times the permittivity epsilon naught times r sub p squared. We can rewrite it by multiplying the numerator and denominator by radial distance, but that's not of interest to us at this point. Well, we still haven't come to a point where this is a coordinate-free system, because this radius is in a spherical coordinate system, and we see we're using a radial unit vector in a spherical coordinate system. So let us go back to our problem and redefine it a little bit. Notice that our dipole was situated on the z-axis about the origin. Let us now take it off the origin, at least its central position, and move it to a different point in space. And let us twist that dipole a little bit So this will be a positive charge, a negative charge. We can draw a line through it. We can identify a coordinate system, which I'm not going to. And let's identify our home base. So this will be X. Let's get this on the screen here. X, Y, and Z. Let us identify, relative to our origin, the central location of that dipole as compared to either the positive or negative charge. And let us identify this as being equal to the position of our source. The only difference between Coulomb's law and our way that we define the position vector, in Coulomb's law, it was pointing from the origin to a specific charge. But we have two charges. Which charge do you choose? Well, maybe we choose a different representation of a point that these two charges are connected to, and that's the intermediate position. It makes sense, because that's what we used here at our origin of our coordinate system. Let us point our point of observation. Let us assume that our point of observation is point P, and it's located at that position in space. Let us identify its location, and this is with respect to the position vector of our point of observation. And our last step is to point from the source to our point of observation, where this is the relative position vector, but of a slightly different form. Here, the relative position vector R, in this particular case, points, let's write it out, relative points from an intermediate point on a line connecting the original charge in this case, this is a dipole, so there are both charges are original charges. Connecting the positive and negative dipole charge. Okay, so relative position vector points from an intermediate point on the line connecting the positive and negative dipole charge to the point of observation. And for clarity's sake, this distance here, vector distance, is our electric dipole vector length, and our electric dipole is pointing in the same direction. Okay. Let's move this up a little bit so you can read it and see it. If we look at this expression, that tying all the pieces together, our potential V at our point of observation can now be expressed as being equal to the electric dipole moment dotted into our relative position vector r all over 4 pi times the permittivity epsilon naught times that relative position vector, actually distance, and now I just have to check something. Yeah, this comes out, no, that stays here, and this is going to be Q. If you look at this formula, and this formula is the one that's down here, sorry about that. Here. We see that that formula is a coordinate independent formula. R points from the source to our relative position in our source to our point of observation. Doesn't require a coordinate system to we can use any coordinate system to define that relative position vector. The relative distance is the same as well. We don't need to have any special coordinate system to determine distance. And the pointing, not wrong course, and the polarization P is a definition. And it's well-defined definition in terms of pointing in the same direction as D, from the negative charge to the positive charge in our space. So this particular expression is a coordinate-free expression, and we can identify it as being a physical law. Just like Coulomb's law is a physical law. Okay, let's get back to our problem now. And we are not going to use any of these special notations. We're going to go back to our original notation. And let me see if I can find it. Just hold on. We're going to go back to this point here, where everything was expressed in terms of a spherical coordinate system. Our task, we now have an expression for the potential. Our task is now to determine an expression for the electric field. So I'm going to, for clarity's sake, write down what our potential is and this is a potential for the dipole, it does not satisfy the problem at hand though. And you'll see that shortly. So we'll say recall. Just give him, yeah, I think it's better. Recall the potential V evaluated at our point of observation in a spherical coordinate system was equal to Q times D times the cosine of the angle theta sub P divided by 4 pi times the permittivity times the position R sub P, I should say distance R sub P squared relative between the point of observation and our origin. Now we want to determine the electric field, and the electric field is equal to the negative of the gradient of the potential and I'm going to put in the appropriate functional dependencies. This represents our electric field at our point of observation. And here we are evaluating our potential at our point of observation. Consequently, we are looking at changes about the point of observation. There is no source or source terms in our expressions. Let us write out, and I'll leave it up to you to perform the appropriate mechanics. In a spherical coordinate system, this is equivalently equal to the negative of the quantity, the partial derivative of our potential with respect to R sub P. This will be in the radial direction, which is a function of theta sub P and phi sub P, take care of one term, plus 1 over R sub P times the partial derivative with respect to the conical angle theta sub P operating on our potential V, and that will be in the conical direction, which in turn is a function of theta and phi. And I made a mistake in notation here. The conical angle itself has no notation associated with it. It just has a functional dependence on where that notation comes into play, plus 1 over R sub P times the sine of theta sub P, looking at variations with respect to the azimuth angle out our point of observation operating on the potential V, and that will be in the phi direction, which is a function of phi sub P. If you perform the mechanics, one can show that's equal to our charge Q times our distance of separation divided by 4 pi times the permittivity of free space times the permittivity of free space times r sub p cubed times the quantity 2 times the cosine of theta sub p in the radial direction, function of beta sub p and phi sub p, plus the sine of theta sub p in the conical, in the azimuth direction, in the conical direction. And that has a functionality as well. And I'll put that down here since I'm running out of room. This will be theta sub p and phi sub p. We have now successfully calculated the electric field as well as the potential due to a dipole, where we impose one restriction, and that restriction is that the distance of separation must be small compared to the distance from the dipole intermediate point to the point of observation. Now, let us finish satisfying this particular problem, which is the point charge above a conducting plane. We now impose the model and force the model to be equivalent to the physics. Therefore, the potential V, a function of our point of observation, is going to be equal to, in the upper half space, it's going to be our electric dipole moment dotted into r sub p divided by, so I'm multiplying and dividing through my expression by our radius, 4 pi times the permittivity of our medium times r sub p cubed. And this is going to be valid for r sub p being much larger than our distance of separation, and the conical angle theta must be greater than 0 and less than pi over 2. And elsewhere, it can be either 0 or a constant, because we have the right to choose our ground to be at any point. So this would be a constant, and that will be valid for r sub p, again, much larger than d, and actually this qualification doesn't even come into play anymore. And theta is going to be equal to or greater than pi over 2 and less than or equal to pi. And like I said, the only constraint here would be the constraint on conical angle. This one doesn't come into play because we didn't use the theory to characterize the potential in this portion of space. It was already determined for us based on the problem statement. Okay, so let me extend this down. That takes care of the potential. Now let's write down what the electric field is. The electric field is equal to, and again we have two solutions. One solution is our charge Q times our distance of separation between the charge divided by 4 pi times the permittivity of free space times r cubed, or r sub p cubed, times the quantity 2 times the cosine of theta sub p, and that's in the radial direction, plus sine of theta sub p in the conical direction. I'm not going to write out the functional dependencies on the unit vector. You can always go backwards in the problem statement to see where they came from. And this is valid for r sub p being much, much larger than the distance of separation between the two charges, and theta sub p to be greater than or equal to 0 and less than or equal to pi divided by 2. That's one solution. The second solution, in the lower hemisphere, it's equal to 0 because the electric field cannot be supported by a metal structure. And if we're inside that metal structure, the field is 0 because the nearly free electron model and the charges are in a lowest energy state. So this will be for r sub p being anywhere. So let's say all r sub p for theta sub p greater than pi over 2 and less than pi. Okay, so I'll give you a chance to look at that. That takes care of our discussion on the electric dipole. What's important on the electric dipole is that we are going to be making use of it to model dielectric mediums, or mediums that are non-conducting, insulators if you like. Inside these mediums, we have dipoles that can twist and turn, they can be compressed, they can be expanded with the presence of an outside field, and each one of these little dipoles makes up the matter or geometry of the dielectric component or dielectric material that you have in mind. Material like wood, such as the desk that I have in front of me, is a dielectric. Plastics are dielectrics. We can have papers being dielectric. Water is dielectric. It doesn't have to be a solid. It could be a fluid. It could even be a gas. For a gas, you would use a model to characterize that gas as being like a fluid, and therefore you can make it, you can give it a dielectric or a modeling dielectric parameter. So this will be coming up in our next set of lectures very shortly. First, we'll be talking about materials, and then we will talk about boundary conditions, and then we're set to open to solve a number of different types of problems using different types of techniques. Okay, let me think now what else was covered in class. I covered the problem that we covered last time we met, and that was dealing with the concept of the electric field and relating it to potential. And if our electric field, or if our potential is at certain points in space, such as the origin or on an axis, we have a tendency of losing a flag, if you like, that would help us determine variations in that particular parameter so that we can perform a gradient process. So that we've already covered. And we went over that in class today, and that's what I went over with you last time. And I think that's pretty much it for today. You have any questions for me? You know, I wish I could give you these sheets. Actually, I could give you these sheets of paper. Would that be of any use to you?
I wrote down most of it already, and I have the video recording.
And sometimes I don't move the paper up and it goes off the screen. But
Yeah.
did you still get enough of it?
Yeah, I managed to write down everything in time.
Okay. Then
It's just me
go ahead.
needing to, again, just conceptualizingly understand it, like, I guess in practice.
This is all practice. Finding
Yeah.
the potential to the dipole is just the simpler part. Trying to find a force on a dipole, you use all these expressions.
Right.
But one thing that you should find interesting is that the potential varies as 1 over r squared for a dipole, whereas for a point charge, the electric field magnitude varies as 1 over r squared. Therefore, the potential due to the electric field due to a point charge varies a little bit faster, which is pretty much what we stated in one of our earlier lectures.
Right.
Well, if you're satisfied, then let us stop here and we'll do something on Friday. Now, Friday is going to be a tough day for me. I have 3 interviews that are being conducted that I have to be at. I teach the class in the morning. I have office hours. So I would suggest 2 sets of office hours. I would suggest doing this. Keep your eye out for the lecture notes. They'll be out either today or tomorrow. And see if you can work through the lecture notes. And if you have some difficulties, maybe you can ask them during the session that we have, office hour session.
Yep.
Seems like people were happy with what last office hour, and we only had maybe 15 minutes or between 15 minutes and a half hour, which means it gives us a whole half hour to answer whatever questions that you have.
Sounds good.
Okay, then let's do that.
Okay, that will work.
Then
Thank you so much for all this.
Okay, I wish the very best for you, and I hope you guys stay healthy and safe down at your end.
Yep, and I hope you are
Right now.
safe as well.
Thank you. Bye-bye.